As an example, we have a look at a hydrogen atom. So what is a hydrogen atom? A hydrogen atom consists of a nucleus, positively charged, and a negatively charged electron, which moves around this nucleus, maybe like this. So if you describe this quantum mechanically, this system, then you use a Hilbert space L2 of R3, and the Hamiltonian takes this form, consists of a Laplacian here, a differential operator, there are some constants, h bar is Planck's constant divided by 2 pi, a fundamental constant of nature. M is the mass of this electron here, and E, that's the charge of this electron, absolute value of this charge, also the charge of the nucleus of this atom, this hydrogen atom. Now, this term here, this is a so-called potential, and it describes the attractive force between the nucleus and the electron. What's this R? This R is the absolute value, the length of this 3-vector x here, and this 3-vector x points, say, from the nucleus to the electron. So this force, this attractive force between nucleus and electron depends only on the distance, but not on the direction. So there's a symmetry. The system is symmetric under rotations and, if you like, also under reflections. O3 would be the symmetry. Now, if you solve this eigenvalue problem for this Hamiltonian up here, you find that you can label the eigenstates by a bunch of numbers, so-called quantum numbers, and they have some names in physics. So there's one number that takes values in the positive integers. That's called the principal quantum number n. Then there is this number L, which runs from 0 to n minus 1 for a given n. That's called the angular momentum quantum number. And then there's this number m here, which runs from minus L to L, the magnetic quantum number. And you solve this system by expressing the wave function, which is a function of this x here, in spherical coordinates, r and 2 angles, theta and phi. And it doesn't really matter for us right now. These are spherical harmonics, and these have something to do with some special orthogonal polynomials, but never mind. So the point is just that the eigenstates, the eigenvectors of this Hamiltonian can be labeled by these quantum numbers. And now when you go on and analyze this system a bit further, then you find that for any central force problem, the Hamiltonian is invariant under O3. So what do I mean by central force problem? I said here the force between the electron and the nucleus is described by this term here, and it's a central force problem if this term here only depends on R, but maybe in a different way. So for all Hamiltonians where this term here at the end only depends on R but not on theta and phi in spherical coordinates, we would say it's a system that's invariant under O3, under spatial rotations and reflections. And well, states for, say, fixed n and L, but m can still run from minus L to L. These transform in a 2L plus 1 dimensional irrep of O3. And the energy does not depend on m. So you have this 2L plus 1 fold degeneracy in the spectrum. And that's the degeneracy you expect for any central force problem. You could look at r squared instead of 1 over r or some other potential here. Now for the hydrogen, when you solve this, you find something else. You find a higher degeneracy. You find that the eigenvalues don't depend on this L either. They really only depend on n. So you have this expected 2L plus 1 fold degeneracy because it's a central force problem because of this O3 symmetry. But now we can let this L run from 0 to n minus 1, fix n, and you get the same energies, same eigenvalues for all these values of L. And that sums to n squared. So you have an n square fold degeneracy for fixed n instead of a 2L plus 1 fold degeneracy for fixed n and L. And that's more than expected. So this is an example for such an accidental degeneracy which we didn't expect by just looking at the symmetry. And then in the end, if you analyze this further from the symmetry point of view, you find that actually the symmetry of this system is a higher symmetry. It's higher it's more symmetric than just this O3 symmetry. There is actually a hidden O4 symmetry. And now if you look at this degeneracy from the representation theory point of view, then you would rather say that these subspaces with dimension n squared, eigenspaces of the Hamiltonian, they carry irreps of some group O4 and not just of the group O3, which would lead to these degeneracies here. And I said it's not just an example, it's also an outlook, because you already noticed that O3 is of course not a finite group, and we will have to generalize what we're doing here to some infinite groups, but this will work, and we will later understand this whole example even a bit better than we do right now.